Hello, welcome back. The title of this lesson is called Properties of Matter. So in this lesson, we're going to talk about exactly what the title says. We're going to talk about the different types of properties of matter. Some properties of matter relate to how a substance looks, and some relate more to the chemical character. And so again, this is another lesson full of definitions. I'm sorry to hit you with so many definitions. Once we get past these core definitions, we can just start kind of focusing more on solving problems. But we have to crawl before we walk, okay? Now we're going to talk about two different kinds of properties mostly. We have physical properties and chemical properties. They're fairly self-explanatory, but it's important for us to talk a little bit in detail about each one. A physical property is any property that's observed without changing the identity of a substance. Now here you get exposed to my little shorthand way of writing things down. I don't want to write down long, gigantic definitions. You have a textbook probably, and you could look in your book and you could read a long definition, but in my opinion, more words doesn't actually make it easier. Sometimes less words makes it easier. Also, I have my own little shorthand. You know, this means without, and anytime you see a triangle, triangle represents change, and that comes from math in calculus and physics. We use the triangle to represent when any quantity is changing. So I kind of use it in my writing. So a physical property is any observation of a substance that you can do without changing the identity of a substance. So for instance, some examples, the color of a substance. You can determine if something's red or blue color or whatever without changing it. You just observe it, right? You don't make any alteration. What about the odor of a substance? Well, that doesn't really change anything either. What about the density? These are just examples. There are many, many, many physical properties, okay? What about the melting point? And the boiling point, and so on. So when I melt, ice into water, I'm not actually doing anything chemically. It's still H2O. It's just in the solid phase, the ice is locked into place, it's vibrating, but really there's not much movement. And in the liquid phase, the molecules are able to move past each other. So nothing chemically is happening. No, it's still H2O. It's just a different phase, right? So that's a physical change. And so density, that's when you measure something's mass and compare it to the volume of the substance. So instead of just kilograms, you would measure kilograms per cubic centimeter. So you can make those observations without changing the substance, right? If I want to measure something's density, mass per cubic centimeter, then I can do that without altering the substance chemically. If I want to look at its color or odor or density or melting point or boiling point and lots of other properties, then of course I can do that without making a change. It's just a physical property of the substance. Now let's contrast that with the idea of a chemical property. Now a chemical property is a property that describes how a substance changes or reacts. And when I say changes, I mean some sort of chemical change in the nature of what it is you're talking about. So a good example of a chemical property would be flammability. Flammability. Some things burn easier than others, right? Paper is going to burn easier than gold, let's say. Right? But see, the only way you can test flammability is to actually force it to undergo a chemical reaction and try to see how flammable it is. I have to burn some paper to see how flammable it is. And once I burn the paper, it's combined with the oxygen. That's what burning is, combining with oxygen. And then you have ash. And so the substance you have left over is not the same as what you started with. So the only way to really measure flammability is to make some sort of chemical change happen. So it can't be a physical property. It has to be some sort of chemical property. Another example beyond flammability would be reactivity. And that's a whole can of worms we have to get into as we go farther into this class. But on the periodic table, you have some elements are more reactive than others. For instance, over here on the left-hand side, sodium, if you drop it into water, then there's a chemical reaction that happens that produces some hydrogen and also a lot of heat, and the hydrogen ignites. So if you actually drop sodium in water, it'll actually catch, you'll see a flame surrounding the reaction that's taking place, and you won't have to light a match. It'll just automatically catch on fire. Extremely reactive. But the gases over here on the right-hand side of the table in this column, remember on the periodic table, when you're looking in the same column, you have similar reactivities, or I shouldn't say reactivity, similar properties, okay? But over here on the right-hand side of the table, one thing that we're going to learn is this far right column is actually not reactive, not very reactive at all. And what I mean by not reactive is it doesn't like to participate in chemical reactions. Now, I use words like it doesn't like to react or it does like to react. These elements have no feelings, okay? They don't have personalities, right? When I say it doesn't like to react, I just mean that because of the electric force and the way these electrons are arranged, chemistry really doesn't happen too much. And it all comes down to the electric force and how the electrons are arranged in these atoms basically prevent it from sharing or exchanging electrons. We're going to learn later that pretty much all chemical reactions is going to relate to the electrons around each of the atoms and what they do. Maybe they trade electrons, maybe they share electrons, but any chemistry you have has to involve something to, I shouldn't say all, because you don't like to make generalizations, but almost all chemical reactions have something to do with electrons that are surrounding those atoms. But in these atoms, for reasons we're going to talk about later, in the far right column, they don't like to change the configuration of their electrons. And the reason why, we'll talk later, it's because of the electric force holding them in place very, very strongly. So they don't like to share electrons. They don't like to trade electrons. They don't like to do much of anything but stay to themselves. But again, it's because of the electric force and the way those electrons are oriented. And we'll talk about that later. But on this side of the table, you have extremely reactive things. And you have all sorts of, a manner of reactivity all the way through the table. But you see, the only way I can measure the reactivity of something is to allow it to react. I have to allow these things to react with something in order to see if they're reactive or not. And so reactivity is a chemical property because it's basically describing when a chemical changes or reacts. There's really no way to measure reactivity without allowing it to react, which means to undergo some sort of chemical change. All right, what else? Chemical bonds, type of chemical. I'm just going to put chem here, bonds. Right? So you could say that's a chemical property because some of these atoms on the periodic table like to form what we call single bonds to whatever atom they're reacting with. And some of them really like to form double or even triple bonds. And the only way that you can see what kind of bonds like to form with the elements that's reacting with is to allow it to react, and that undergoes some sort of chemical change. So this is a chemical property. One final example, we're going to talk about something later called an oxidation state. Once again, this oxidation state is all about how it likes to give and take electrons, essentially. Oxidation state of an atom we're going to talk about all relates to how willing is it or how much does it donate electrons to other atoms or accept electrons from other atoms, because as I said, all of chemistry is related to what happens with the electrons which cause things to bond together, okay? So these are all chemical properties. They require a change in the substance, a chemical change, in order to basically measure them, whereas the physical properties, all of these examples, we didn't make any changes, we just observed, okay? Next, we have this idea of an intensive property and an extensive property. So again, I don't have very many words here, but an intensive property is a property that does not depend on the amount of a substance. And it's just going to be easier to write a couple of examples down and show you that. So for instance, the melting point. The melting point of ice, it doesn't matter if I have one little ice cube or an iceberg. The melting point of ice, it's totally independent of how much material I have. You know, most things are actually what we call intensive properties that you might think of. Melting point, boiling point. I'll just put here, boiling point. Right? What else do we have on our list? Density. Because the units of density we're going to talk about later, it's kilograms or some kind of mass unit per cubic centimeter or cubic meter, some mass per unit volume. But you see, the density is because it's mass per unit volume, any substance I'm taking, I'm just going to collect a certain volume of it and then see how much mass is in there. It doesn't really matter about the overall sample because the units of density, I'm just going to scoop out 1 cubic centimeter and see how much mass is there. It's independent of the entire size that I have because the units of density, I'm just taking a 1 cubic centimeter anyway to look at it. What about the temperature of a substance? If you measure the temperature, in this room of a block of wood or a gigantic log of wood, right? Is the temperature of those objects dependent on the size of the objects? No. If you put an object in a room and you leave it there long enough so that all the temperature variations settle out, maybe several hours later, the temperature of a substance doesn't depend on the size of the substance. It depends on the temperature in the room. The heat, flows in, or the temperature goes up, and once it all settles out, everything in the room more or less should be at the same temperature. Okay? So these are called intensive properties. Okay, you can compare that with the word extensive. So extensive is sort of like external. Intensive is sort of like internal. So these are like internal properties that are just properties of the substance. It doesn't matter how much of it you have. It's just always going to be true for however much of the stuff that you have, right? Most of the properties you think about are intensive. But we do have properties that are extensive in nature, right? What about the mass of an object? Well, the mass of an object is measured in kilograms or grams, right? If I have this much of some lead, in my hand, or if I have this much of lead, holding on with two hands, it's going to be extremely heavy. The amount of mass is totally different, and the reason it's different is because it depends on how much of the stuff I have in my possession. Of course, the more atoms you have, the more mass you have. So mass is what we call an extensive property. What about volume? Right? Volume depends on how much stuff you have as well. If you have, this much water versus this much water, the more volume of water you have, it depends on the amount of water that you have. Because volume, unless you're compressing it or doing anything weird, the volume of water you have is related directly to the amount of atoms that are in there, essentially. So these are just definitions. You can use them when you're talking intelligently to people, but otherwise they don't really impact how we do our chemistry. But they are important because as we talk about things, I might refer to something as an extensive property or an intensive property, and you need to know what that is. All right, now we have a few more. Let's talk about physical changes and chemical changes. And notice I didn't even write a definition here because I just want to jot down a few ideas. Now that you know what a physical property and a chemical property is, I bet you could guess what a physical change and a chemical change actually is. Well, a physical change would be a change in a substance that doesn't relate to its chemical nature. Something physical that changes about its appearance without changing the microscopic arrangement of the atoms of the substance, because that would be a chemical thing, right? So a physical change, the best example, is when you go from a solid to a liquid. Think about ice melting, right? Or if you go from a liquid to a gas. Because in all of these cases, it's still just H2O. A long time ago, before we really knew the nature of molecules and atoms, of course they thought water and ice were totally different things. They had no idea what was going on. But now we know that if you could zoom in on a molecule inside of the ice crystal, and if you could zoom into the molecule inside of a glass of water, the molecule looks the same. It's still H2O and it has the same shape. But if we cool down the water, the molecules stop moving, or they slow down, and eventually they get to the point where they just get locked into place, into a lattice there that we're going to talk a whole lot more about later, eventually where they can't move past each other anymore. They vibrate a little bit, but they can't slip past each other anymore. And so we call it a solid in that case. But the chemical nature of H2O, of which that substance is made, it doesn't change when you go through a phase state like that, change like that. If you go into a gas phase and you have water vapor coming off as you boil in the water, it's still H2O. That's a physical change. So in contrast with a physical change, a chemical change, you might guess, is basically when you have some sort of chemical reaction. So I'm going to say some sort of reaction. And we're going to write down many reactions throughout this class, but I'll just give you a spoiler ahead of time. A chemical reaction is when you mix two or more things together, some electron transfer happens or sharing happens, and because of that, you get bonding, or sometimes things can break apart, and so the products you get might be combinations of the reactants, is what we call it, the things that you mix together, and you may have new substances formed. But those are chemical changes because there's electron transfer or sharing happening, causing things to be bonded together. We'll talk a whole lot more about that, but that is in general what a chemical reaction is. It's a rearrangement of the elements. So I'll put rearrangement. Rearrangement of the elements. Or just a combining of the elements. Hydrogen coming together with oxygen, of course they bond together and they form water, right? So the best example that everyone is familiar with here would just be burning. Right? Burning. If I take a block of wood and it's sitting in an atmosphere that has oxygen in it, which is where we live, and I apply heat, because the heat's required. We'll talk about why later heat's required to get burning started, but heat is going to be required to start the reaction. But once the reaction is started, you no longer have to apply more heat, because the burning process releases heat, and the heat that is released can continue the process of sucking more oxygen in and continue the combination. But what's happening molecularly is the atoms are coming from the wood, the carbon and other things, and they're combining with the oxygen and forming carbon dioxide, CO2, and water, H2O. It's a rearrangement of the atoms. The oxygen's coming from the air, hydrogen and carbon are coming from the wood, and they're rearranging into CO2 and H2O. And the products look totally different than the two substances you started with. So that's a chemical change, right? And we talked about, hydrogen plus oxygen, and it yields H2O. And we're going to talk a whole lot more about this. We're going to talk about how to balance a chemical reaction. We're not doing any of that yet. We're just saying chemical reaction, rearrangement, or combination of things. It's all happening because of electrons doing their thing, either being shared or exchanged down at the level down there. So that's a chemical change, right? And wood burn, I guess I'll just put wood burning usually leads to CO2 and H2O. That's what's usually floating up from your campfire, right? All right, the last few things we want to talk about before we do our quick problems here is, since we've talked about physical changes and chemical changes, now we're going to talk about separation of mixtures. It's kind of just thrown into the end of this lesson. It's really, honestly, not all that important, in my personal opinion, but we do need to cover it because you're probably going to be asked about it. We talked about mixtures. Mixtures are when things are mixed together, but there's no chemistry happening, no electron transfer, no bonding. It's just two things mixed together, like rocks and water. If I have a bucket of water and I pour rocks in and I stir it up, well, there's nothing chemically happening. The rocks are still at the bottom. It's just a mixture. Or sand is a mixture. Or flour. If you put flour in water and mix it, there's no chemistry. It's just a mixture of two different substances, right? Well, how do you separate mixtures? Once you have a mixture, how do you separate it? A better example of a mixture would be a solution. You know about this. If you put sugar in water and stir it up, what happens? The sugar dissolves. It doesn't go away. It's still there. It's just that the crystals are broken down and they're basically fitting in between the water molecules. And so the water molecules are now crowded because there's a little tiny chunks of sugar in between all the water molecules. But it's a mixture because they're not bonding to the water, but they're just kind of broken down and hanging out between the water molecules. How would you separate this mixture into its core components again? Well, a very important one to understand, the most important one on this list, is something called distillation. You may have heard of the word distillation. What you can do is you can take a flask, right? Let's say you put a flask here, something like this. And what you could do is you could put in this flask your water in either salt water or sugar water or whatever, here. Let's call it salt, because we're going to learn later sodium chloride is salt, and then plus water. And that's what's in this flask. And what you can do is you can have another flask that's a little bit physically lower over here. And what you can do is you can connect these guys together by a tube. And sometimes the tube has got like the curly, you see on TV sometimes, like the mad scientists, like the little curly tube there. And what you can do is you can put a flame under this and heat it up. So that's why I didn't write a definition here. Distillation is when you take a solution and you heat it up. What's going to happen when you heat it up? Well, the salt water solution is going to get warmer and warmer and warmer. Eventually, the water molecule, some of them will start to escape from the top. That's called boiling, right? But the salt doesn't escape. The salt is a totally different substance and character. It doesn't go to a vapor phase. It stays in the solution down here at the bottom. So what happens is the water vapor goes up. It's very hot. And when it goes down this tube here, it starts to cool off. So I'm going to put down cool off. And why does it cool off? Well, it's because you're getting farther away from the flame. Maybe you can even have an ice bath. You might actually have an active cooling where you have an ice bath around that tube. So the water goes up and it goes down here, and then droplets start forming and it condenses down and starts to drip, drip, drip into here. And then what you have here is pure H2O. So when you buy distilled water from the store, what it is water that has been boiled, the vapor has been collected and then condensed back again into, your fresh container. And what is left behind? All the impurities are left behind. Any salt, any mineral, things that are dissolved in the water, they get left behind. Eventually, when there's not very much left here, you just throw this away and you start over with another bucket of it. So if you're stuck on a desert island and all you have is salt water and you can't drink salt water, and if you have glassware available on your shipwreck, then you could distill it. All you have to do is boil it or very gently cause the vapor to come up and somehow cool it back down. That's the tricky part, getting it to cool back down and collect it again. Then you will have fresh water. Now, this process, distilled water, this process is happening all the time. We call it the weather. Because see, everything, the rain comes down, right? Makes puddles of muddy water. Everything's disgusting. You wouldn't want to drink that water, right? But then the sun comes out and then it dries up all the rain and the itsy bitsy spider comes out again, right? So basically the sun comes out, the puddles start to evaporate. They're not boiling vigorously, but they are very slowly evaporating, eventually go back up into the sky, collect and come down as rain again. So this whole process of distillation is kind of happening on Earth all the time. And so the water coming down from the clouds is relatively, I wouldn't say go drink it, because you never know. It may be picking up dust particles on the way down. But in an ideal world, it would be relatively clean water coming right out of the sky. That's called distillation. It works best when you have a solution of something dissolved in it, you cool it down there. Now, filtration, I'm not even going to draw a diagram because it's so simple to understand. Filtration is exactly what you think of. You put like a coffee filter or some kind of mesh filter or a colander or something like that, and you pour your mixture through it, and the liquid can flow through the holes, but the filter paper or whatever catches the solid material. It works best for solid things, like if you had water and sand, let's say, then that would work great. You would pour it through a filter and this filter would catch the sand because the sand cannot go through the filter, and you would separate the mixture that way. It doesn't work so well for items dissolved, like salt dissolved in water, because the salt is broken down so small, it's going to go right through the filter. So it doesn't work so well for that. You should use distillation when you have a solution in general, when you're trying to clean up a solution and purify it. But when you have large particulates of solids, filtration works great. And then we have the last one here called chromatography. And that one's not one we're going to spend much time on, but chromatography is basically, the origin of it is trying to take the pigments out of various materials. It turns out that if you filter a solution with pigments in water and you allow it to go down a very long, kind of like lab equipment, with a filter paper there as well, it turns out that the speed of the water and the speed of the pigment, they're not quite the same. And if you let it travel over a long distance, then the paper is not so much filtering it out as it is the distances that they're allowed to travel are different. And so the water can the clean water can make its way to the end and the pigments get stuck to the paper. So it's kind of like filtration, but it's a little more elaborate than just pouring it into a filter and allowing it to catch it. You have to have a special apparatus with a very long piece of chromatography paper. It's a whole special setup, but basically it comes about, let me just make sure I'm saying everything I want to say. Pigment in solution will stick to the filter paper and not flow at the same rate. It will basically get quote unquote sucked out of solution because over a very long distance that paper can catch a little bit of that pigment. And then the pure water can keep going. But you need a very elaborate setup for that. That's why it's called chromatography, chroma meaning color. And so originally it was used to basically pull pigments out of whatever it is you're trying to purify, all right? All right, now what we're gonna do is, since we now know what physical properties and chemical properties and intensive properties and extensive properties and physical changes and chemical changes are, now we're gonna solve a few quick problems, and they're gonna be very simple. We're just gonna answer some questions, basically. All right, so what we're gonna ask here for problem number 1 is we're going to say a scientist is attempting to characterize a substance and makes a series of observations. Classify each observation as a physical property or chemical property. There's a bunch of words that basically says, tell me, here I'm going to list a few things. Tell me if it's a physical property or a chemical property now that we have defined what those are. The first ones, the substance is metallic, white, silver color, and shiny. So it's white, metallic, white, silver color, and shiny. So we talked about physical properties, and we talked about chemical properties. You have to change the item in order to figure out if it's chemical property, but we're not doing that. This is, the color shiny, things like that we can observe without making any change. So that's a physical property. So the first one is physical property. Physical property. All right, part B. A substance melts at 649 degrees Celsius and it boils at 1,105 degrees Celsius. Is it physical or chemical? Well, melting points and boiling points are all physical properties. You're not making a molecular change by boiling it. That's a physical property, as we've talked about before. So boiling and melting are always physical properties. Right? What about C? A substance burns in air and it reacts with chlorine. Is that physical or chemical? Well, when something burns, you have to change the physical character of it to measure how it burns. Also, reacting with chlorine means it's combining with chlorine. You're changing the chemical character of it. That is a chemical property because it describes how a substance changes or reacts. So this is a chemical property. Okay, what about D? A substance can be hammered into sheets and drawn into wires. Is that a physical or a chemical property? Well, that's a physical property. You're not making any molecular changes when you do those things. So that is a physical property. Okay, and our last one here for this problem, the substance can conduct electricity. If you measure, if a wire can conduct electricity, are you making a chemical change? Is something on the very lowest level changing chemically about what it is? No, that's a physical property. That's a physical property. All right, that effectively constitutes problem number 1. All right, problem number 2. Of the changes below, which ones are physical and which ones are chemical? So same kind of thing, but slightly different flavor of ideas here. So first part of it, part A, boiling canned soup. So if you take soup, put it on a stove and boil it, is that a physical or a chemical change? We're talking about not properties, but changes, physical or chemical changes, right? Well, a chemical change is some sort of reaction. You're not doing a reaction by boiling it. You're just changing the state by causing it to boil. So we're going to say 2A, that's physical change. Okay. All right, part B, toasting a slice of bread. Now you might think that that's a physical change, but actually when you think about it, when you put something in a toaster and it turns brown like that, what you're doing is you're microscopically burning the surface. Oxygen is combining with the surface and it's changing color and you can't reverse it back. You can't reverse toasted bread back to perfectly untoasted bread. You can't do that. So that is an irreversible change and it's a chemical change. So that's a chemical change. I'm going to put triangle for change. As I told you, I'm going to be doing that a lot. All right? Part C, chopping a log. So here I have a log, I chop it in half. Is that a chemical change or a physical change? It's just changing its appearance, its size. So that's obviously a physical change. Right? And then part D is burning a log. Burning a log is when you combine oxygen with the log and it totally changes it chemically to something different, CO2 plus H2O usually, and so that's a chemical change. All right, that is problem number 2. All right, let's take a look at problem number 3. It says, in order to separate the components of sugar and water solution, would it be best to use filtration or distillation? We kind of answered this in the lecture, but in general, when you have a solution, what's happened is the water has broken down the crystal so that it's not gone, it's still in there, you can taste it, but it's just invisible because it's not clumping anymore, and all of the little bits of sugar, in this case it's sugar, is basically broken down to be in between the water molecules, but they're still there. If you pour that through a piece of filter paper, unless it's a very special piece of filter paper, the bits of sugar that are in between the water molecules, they're microscopic. They're going to go right through the paper. So you really cannot, just go try it. Just go try to catch sugar out of a coffee filter or something. It's not going to work because the particles of sugar that are in there in solution are too small. They're microscopic. So would you use filtration or distillation? Well, we're going to use distillation. We already said that when you distill something, you have in this case I use salt and water, you heat it up, the water it then goes out of solution, leaving the solution behind and the salt behind, then it cools down and it drips purely into another flask. So in this case, it was sugar water. How would you reclaim that or purify that? You would use distillation. All right. And our last problem. Which separation technique does each of the scenarios describe? So here's part A, pouring boiling water and cooked pasta through a colander. So which separation technique, what I'm asking you, is when I separate pasta like that through a colander, am I using distillation, filtration, or chromatography? I'm not doing either of these, I'm using filtration. The colander is acting like a filter to mechanically catch the particles of pasta, effectively, and filter it, and the water goes out the bottom there. So that is filtration. So we'll call it 4A, we'll call that filtration. Okay, and here is our very last problem. How would this be characterized in terms of which separation technique? Refining sugar by removing colored impurities. So white sugar is, what we eat, table sugar, but it doesn't come out of in nature. It isn't white. It is made white through a process. Is that process more aligned with filtration? No, we just said that you basically can't filter solutions like that, okay? Is it distillation? No, because if you just boil the water off, you would just have the same colored sugar left behind. It has to be chromatography. So you can actually take sugar, put it in solution, in a slurry, let it flow over a special chromatography setup, which very, over a long distance can take the colored particles out. Essentially, the speed of the colored particles, the pigments that's in there, is different than everything else, and so over a long distance, it can kind of pull it out. That's called chromatography. A clue here is you're trying to take the color out of something, so that's chromatography. So I'm just going to put chromatography. All right, chromatography. All right, so that's it. We've covered a lot. We've covered properties of matter. In terms of physical properties or physical properties, chemical properties. We've talked about intensive and extensive properties. And then we've talked about physical changes and chemical changes. The reason we need to cover this stuff, and then we talked about separating mixtures with distillation and things. The reason we have to cover this stuff is because very soon we're going to be talking about boiling points and melting points, and we're going to be talking about chemical reactivity and all these things. So it's important for you to know the terminology, so when you read your book, or when I tell you that something is an intensive property, or if I tell you something is a chemical property, you're going to know what that basically means. And so we're building the bedrock here for our future lessons. So go through this, make sure you're getting the right answers to the problems, you understand the terms. Follow me on to the next lesson. We'll continue to build your skills.